Hi, so the first thing I did when understanding this problem is I turned the system of equations into a matrix, and the reason I did this is so that way I could reduce it with row reduction and end up with this nice matrix down here. And what this basically means is that x1 plus 4x3 is equal to -5, and then x2 minus x3 is equal to 3. And using this, I just didn't have to do all that complicated algebra stuff that is easy to mess up. So from there, I solved for x1 and x2, which I got over here, and then I rewrote them in terms of x3, since x3 is our free variable. I then turned that into this parametric vector form by taking these constants, putting them out here. And then the second vector is multiplied by this t value that I created, which is defined as x subscript 3, and then t is equal to my x3 vector. So basically, it's the same thing as up here, but rewritten. X2 and x1 are basic variables. X3 is a free variable. And then for the homogeneous system, it's the same thing, except these solutions over here to these equations is equal to 0 over here. So I rewrote this, and when you get the row reduction, it's the same thing, except these values are 0. And that is because whatever you do here is not going to affect over here. Yep, so then I set this all equal to 0, and then solved for my x1, set this equal to 0, solved for my x2, and we got this, this here. And this is basically our solution to the homogeneous system, but x of 3 can only equal 0 for it to fit this exact one. But we found that this right here is kind of the solution, and then here is a particular solution, if that makes sense. My vector with the scalar t outside of it can be written to a particular solution to a non-homogeneous system, which will be shown geometrically. So I've gone and drawn these, and what's important to notice is the fact that this has the starting point of this origin value. So I'm going to just show down here real quick. So this is the general solution right here. This ax is equal to 0 right here. And this one here is a particular solution. And basically it's adding to this general solution. So where it's starting here is actually going to become this second part. So our second part here is -5, 3, 0. So we're going to look at that. 1, 2, 3, 4, 5. Okay, 1, 2, 3. So this is our new starting position. This is our new x3 is equal to 0 starting position. But right here on this line, x3 is equal to 0. So basically, like, geometrically, we have moved this spot to here. Let's get my little ruler out. There we go. Okay, so 1, 2, 3. There. I'm failing this so badly. 1, 2, 3. So these two are also moved by this vector. This vector that is pointing from here to here. And every single point on this is moved. Like, I'm going to just say that this is x3 is equal to -1. Sorry, I'm like, yeah, we're going to go -1 because that's the z-axis. So we are going to say that's -1. And then this would also be x3 is equal to -1 at that point. Another important observation to make is that the distance between these vectors is that -5, 3, 0 vector. And that all of these vectors that we are making in between them is that vector that we have created the new 0 position to. Yeah, so let's just theoretically say that we wanted to change this vector matrixy to equal a different output. I could have, theoretically, this t have any starting position. So this could be A, B, C. And just by moving this here, this bit, and we're going to move it. So A, B, C. I can move this to the position of A, B, C wherever I'd like it.